Hi everyone. I apologize for not noticing that my microphone was not working properly during the presentation. And I apologize for those of you who are online watching. I'm going to try to record this audio track and combine it back with the video. It won't be as rich as the original, but I'm hoping this will be sufficient. So this is a new topic this week. We're talking in lecture 13 as well as next time, next lecture 14 about soils. Today we're going to talk about soil basics as listed on the slide here, kind of what makes the materials in soils, what are the structures of the various horizons in soils, and we'll go through some examples. And then next time we're going to talk about contaminants and remediation in soils. So there's a lot of different things that happen in soils, including here in Hawaii. These are just some images I've taken from the local news. We interact with soils in a lot of different ways. Obviously, for agriculture, we have areas on the land surface that have suffered from land use practices in the past that are being reforested. We have massive erosion issues. And of course, we have conditions where contaminants have been dumped into the environment. And each one of these things and the impacts of them is a reflection of kind of the soil composition and the soil attributes. So this is a table from a soil textbook about some of the things that go on during soil formation. The top three things on the list are things that pretty much always happen. We always have weathering, we always have the addition and decomposition of organic matter, and we always have the formation of structural units. This is what define a soil. Then there's this list of all these other things, numbers 4 through 10, that sometimes happen. They don't have to happen for a soil, but they are very common. These include processes such as leaching and the addition of acid, the washing of clay particles, and by this we're talking about clay-sized particles, down through the soil column to accumulate near the bottom, the process of transporting of organic carbon complex iron and aluminum down through the soil horizon, the leaching of silicon in some cases, and this is very related to the presence of organic matter, reduction and or oxidation, and we'll talk more about these conditions as we go. The accumulation of salt, especially sulfate and chloride salts. This is primarily due to the addition of water followed by cycles of evaporation, especially in arid regions where we have agricultural soils where we're irrigating. We can add a lot of water and have a lot of evaporation and have a fairly rapid buildup of salt, as well as alkalization and erosion. I guess I had something else to say here, which I forgot, which made me go on and talk more about this slide. I'm just going to wait until I go on to the next slide. Okay, so this is an introduction to the kind of materials we find in soils, and I want you to think about them as a gradient of conditions from stuff that we find typically at the surface to stuff that we find at depth. Every soil column and soil horizon varies for a variety of factors, which we will talk about. But in general, what you find is that at the top of the soil, it's going to be the least like the rock material from which it was derived, and the most organic rich, and generally the most acidic of all the materials in the soil column. And when we go down with depth, we reach a horizon where there is essentially no organic matter present, and it is the inorganic weathering product of rock at depth. It's a horizon that we call saprolite. Saprolite is an inorganic weathering product, the breakdown of the primary minerals and rocks. This picture I'm pointing to happens to be a place where a saprolite zone was exposed at the surface by erosion. So that's why you can see plants growing right on it. That's not a common process that usually occurs down at depth. But the important thing to recognize is that there's this gradient. And in the intervening layers between them, we have various changes in composition, structure, texture, and other properties that reflect how they are formed. We'll get into that more in a moment. This is just one little bit of note about three of the primary trace metals that are required for a terrestrial ecosystem for the living plants on the land surface: calcium, magnesium, and potassium. And you can see the breakdown in terms of the relative proportion of those elements found in plants, in the living biomass, the relative amount found in exchangeable ions. These are sitting on exchangeable cation sites on clay particles, as we talked about last week and in preceding weeks, and what is in the primary rock materials that can be liberated during the process of weathering. Now, what you will find, which is so interesting, is that the relative proportions of these three elements are pretty similar in the parent rock, but you can see there that a much greater proportion of potassium relative to magnesium and calcium is available on the exchangeable ion surfaces. And relative to the plant demands, potassium is highest in a lot of soils. You might even argue that this is why ecosystems have developed to have more dependence on potassium than some of these other elements over time. But importantly, when we do things to soils that change the exchangeable cation status of the clay minerals, which are the primary repository for them, plus minus organic matter, which can also hold some of these things, we can change the availability of these important nutrient cations for plants. We'll also talk later in the semester about how addition of hydrogen ions from acid rain can replace these exchangeable ions on clay minerals and take their place, therefore reducing the ability of the soil to hold these important cations, which are required by the plants living on the land surface. I'll also note that this histogram is for a relatively well-developed soil in an area where a tree was planted, or a series of trees, 150 years prior. So in terms of what our soil is made of, we can find two kinds of materials, primarily inorganic constituents. These are minerals. They come from the breakdown of rocks. And we can have various types: clays and oxide minerals and silicate minerals, and we'll talk about them on the next slide. Plus, we can have organic materials, and these are derived from the flora and fauna living on the land surface and under the land surface, including by microorganisms. So typically, a soil has about 5% organic matter. Some can have way more than that, and some can have less. That's a typical proportion, and it's this addition of organic matter that helps define this material as being a soil. Now, the inorganic solids have three primary forms: very resistant primary minerals that come out of the original rock. These are things like quartz and titanium minerals like rutile and sphene that just don't break down very quickly in the presence of water. Then we can have alteration minerals. And as we talked about earlier in the semester, these are incongruently formed by the dissolution of primary minerals, whereby we leach some chemicals out and we make new minerals in their place. These are typically things like clay minerals and oxides and hydroxides, commonly called oxyhydroxides as a category. And finally, precipitation minerals, things that salt out of solution, like carbonate minerals, as well as some hydroxide minerals like iron oxyhydroxides. Okay, so now this is a ternary diagram showing you some of the physical characteristics of soil. In this case, it's the size fraction of the grains. So there are three types of sizes of particles. These are not compositional attributes. The sand, clay, and silt are three sizes, which I'm pointing to there on the screen, and they represent different sizes of grains, as I say, and you can find soils with all sorts of characteristics. You can find soils with equal numbers of grains in each of these sizes, or soils that primarily only have the smallest, the silt-sized particles, or soils that only have the largest or the intermediate one. And interestingly enough, this affects things like how water drains through the soil, the relative porosity of the soil column, which is the amount of space between the grains through which water can pour through and organisms can move and develop. And as we will see when we talk about groundwater in the following week, the way in which soils are composed, not only the size fraction of the grains, but the variation in the size fraction is going to determine characteristics of water flow, of saturation, and therefore how chemicals move through the subsurface. So how do soils form? Well, there's a variety of processes involved, some of them physical, some of them chemical, and some of them biological. All of these are included in the term that we call weathering. And weathering, the process of taking primary rock and breaking it down to make a soil, is almost always mediated by water, which means there's water present, and the soluble components of this process are taken from the solids and put into the water, leaving behind new solids. So that when a soil is produced, we change the solids that are present on the land surface for ecosystems to interact with, as well as the composition of water, which will percolate through the soil column down into the saturated zone and eventually form the basis for groundwater leaving that system. So this process that happens in soil columns is very important for determining the chemistry of various aspects of the geosphere, biosphere, hydrosphere system. Not sure what else I'm saying here. I'll wait until we get on to the next slide. Obviously, I've had a lot to say about this slide. Kind of forgotten what it was. Dum 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 dum. Okay, so this is just a simple slide showing you some of the various processes that can happen during chemical weathering. And I've had a little addition here to include organic chemicals, obviously produced by organisms, but they're also important processes. So this slide shows you three different ways that microorganisms in the subsurface are important in the weathering process and the transport of important nutrient elements from the solids in the soil up into living plants on the land surface. There's three examples here. One of them involves organisms producing organic acids, which attach onto solid primary mineral surfaces and cause them to break down and allow for the release of metals into solution in the form of primarily of cations, as you can see there. And this is a very important process that's sped up by organisms, as well as processes which we talked about earlier in the semester that are responsible for the storage and transformation of nutrient elements, nitrogen and phosphorus, to make them both bioavailable. And this includes things that break down partially fixed nitrogen and phosphorus in the form of organophosphorus and organonitrogen compounds, as well as oxidation reduction reactions on nitrogen that help transform them into usable forms. Now, weathering itself has a lot of different processes that are involved with it. The rates at which we alter a primary mineral to something called an alteration mineral involves many different factors, but the three primary ones are all related to climate, namely the temperature, the availability of water, and biome factors. So, how warm or how cool it is. It turns out many minerals, the rates of breakdown and the extent of breakdown are temperature dependent. Higher temperature favors more breakdown. The presence or absence of water, especially the amount of water, can affect the amount of breakdown for solubility limited elements. And biome factors include the production of organic matter that helps make organic acids that change the pH and also make chelating agents that can help with the breakdown. These are all three critical things you can imagine in a warm, wet, tropical environment, such as we have here in Hawaii. All of these phenomena are optimized, and the rates of alteration are relatively quick. They'd be relatively slow in a cool, dry place, such as a dry area in Iceland, even though the rock type in both places is the same type of volcanic rock. Now, we also need to consider that the formation of a soil from this place or that is also heavily dependent on things like what kind of rock do we have in the area, physical factors such as how is the rock composed, both physically and mineralogically? What are the sizes of the grains that are in there? What is the porosity? Are the grains big or small? Do we have freeze-thaw cycles? Can the rock disaggregate into large grains or small grains? What is the nature of the porosity and the fracturing of the rock? And what are the physical minerals in the rocks? Because as we will see in a moment, certain minerals break down more quickly and more substantively than others, leading to changes in the rock substrate that can allow it to subsequently break down even more as alteration and weathering continues. Dum 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 dum. Next slide is coming. Okay, so here's where I asked you all if you remember the Bowen's reaction series, and most of you nodded your heads, a few you didn't. And so for those of you who didn't know, I reminded you and the others that the Bowen's reaction series is something that was developed in the early 1900s to explain how minerals change or evolve in a magmatic system as a function of temperature and pressure. So as a magma starts to cool and rise to the surface, we form different minerals from it. Now, it turns out that from an igneous petrology perspective, we don't really think this happens anymore. We understand that it's way more complicated. But what's interesting about the reaction series is that it's a way of describing minerals as a function of the pressure and temperature of formation. And it turns out that the susceptibility of minerals to alteration varies as a function of how far or how different the conditions of formation are from those at the surface of the Earth. Things with temperatures and pressures similar to the surface of the Earth weather much more slowly than things that were formed at either high temperature or high pressure compared to Earth's surface. It's also true that in the interior of the Earth, we have reducing conditions. So for instance, the iron in most of these minerals is reduced as iron 2+, whereas at the surface of the Earth, we have oxidized conditions where iron 3+ is present. So if a mineral has a lot of iron 2+ instead of iron 3+, it is also more likely to weather more rapidly in a soil column. So when we have weathering, minerals can break down by both congruent and incongruent processes. And this sequence of minerals, in the pink ones on the left-hand side that I'm pointing to now, those are magnesium and iron silicates primarily. And on the blue side of the diagram, these are feldspar minerals, which are sodium, potassium, calcium, aluminosilicates. They coexist together in rocks. And as you can see from that diagram, the sequence of minerals, and the names aren't particularly important, but the minerals that are present change in terms of weathering susceptibility in inverse order to how they would form with temperature and pressure. So for instance, the rocks that we have here in Hawaii are formed at relatively high temperature. They're high temperature volcanic rocks. And so our minerals break down relatively quickly. So including the factors we talked about before, the climate factors, this makes our rocks break down really quickly. Now, this is another way of looking at the major elements that we find in rocks and their susceptibility to weathering in a bulk perspective. This is a very kind of gross simplification, and I leave it for you to read through items 1 through 5 if you want. In the notes, they talk a little bit about the details about the steps and the processes here. But if you think about weathering as a continuous process with through flowing water, you're going to have characteristics where the elements that are most easy to remove during incongruent dissolution and most soluble being pulled out and separated from the elements that are least soluble and most likely to stay behind, either in new incongruent minerals or in primary minerals that are just very resistant to being broken down, such as quartz. So things like silicon on the very left-hand side of this diagram is present in the rock, but it doesn't really like to be dissolved away. Whereas things on the right-hand side of the diagram in green, things like sodium and to a lesser extent magnesium and calcium, they get removed from the rock during incongruent dissolution and moved through with the through-flowing groundwater. Now, those elements in the middle, to some extent calcium and iron, and to a lesser extent aluminum, these elements are intermediate in solubility. And so what happens with them is that as weathering progresses, we can dissolve and then reprecipitate these minerals as a function of the relative amount of water that's present, the relative amount of organic matter that's present, the pH, etc., so that these things tend to move through the system more slowly. So as water percolates through, we pull the sodium and the magnesium and some of the calcium off more quickly than the fraction of calcium that reprecipitates as calcium carbonate, or the amount of iron that reprecipitates as iron oxyhydroxides, or the amount of aluminum that reprecipitates as aluminum hydroxide, also known as gibbsite. This is kind of a simplification, but you can think of all the other elements in the periodic chart as fitting into this category as well, so that many of the sparingly soluble transition metals behave kind of like iron, which I'm pointing to right now, and therefore move through the system more slowly. And as we've talked about before, their relative solubility in the system is greatly enhanced by the presence of organic matter. And if you recall, I said there was a gradient in organic matter in soils from high in the upper part of the soil column to low in the lower part of the soil column. This change in the amount of organic matter also changes the solubility behavior of many of the transition metals, and therefore where we find them in a soil column. And in fact, when we get to mid-depths in the soil column and the organic matter content goes down, this is where we start to see things like iron accumulating in what we call the zone of accumulation, because the loss of organic matter causes it to come out of solution. We also see shifts in acidity, namely rises in pH when we lose the organic matter, which also causes calcium to precipitate as a calcium carbonate. And we'll talk about both these processes in more detail on an upcoming slide. Again, I seem to have had a lot more to say about this slide in class than I remember what I said. So we'll just wait. Sorry for the silence, but I'm just going to keep talking over this same video. And I'm not going to go on to the next topic until the next slide comes up. Okay, so this side has two diagrams, the upper one and the lower one. There's a bunch of different mineral names on here. I don't want you to have to memorize any of them, but I'm pointing to right now are what are called primary minerals. These are things that we find in igneous and metamorphic rocks. And everything in those colored boxes are alteration minerals. And there's a sequence as we move further to the right across the diagram. These are mostly clay minerals or oxides and hydroxides. And as we move farther across the diagram from left to right, they become more weathered. And if you look at the arrows, you'll see that what weathering means is either the subtraction of cations like calcium or magnesium or potassium, and or the exchange of the relative proportion of things like potassium and hydrogen as we move vertically through the diagram. And if you go all the way over to the right, you'll see kaolin. That's the soil scientist's name for the mineral kaolinite. That is the most stripped out material that I'm pointing to now in that bottom table. That bottom table also lists the charge on layers. If you recall, the week before last, we talked about charge on particles in terms of cation exchange capacity. That's one measure of how much charge a mineral can hold on it. You can also just look at it as the absolute amount of charge. And the very weathered minerals like kaolinite have very little charge on them because so much water has gone through the system that has extracted all of the things that substitute into the mineral that give it exchange capacity in the first place, which is manifested as layer charge. Now, some of those other minerals up the middle, such as montmorillonite, or off on the left-hand side, such as illite, and you can see the structural formulas for them. They're complicated minerals down below. These have higher layer charges. So one manifestation of this process is that as weathering goes on and becomes more intense, or in areas with more intense weathering, higher rainfall, higher temperature, higher organic matter, biome factors living on the land surface, we have more intensely weathered particles in the soil. And those more intensely weathered particles have lower cation exchange capacities, so they can hold less of the important nutrient elements like potassium and magnesium and calcium on their surfaces. Other important cations in this process are things like ammonium. The more weathered a soil is, the more altered its clay minerals, the lower its charges, the more susceptible it is to acid rain addition too. So these are a couple of simple hydroxide or oxyhydroxide alteration minerals. On the left is goethite. It's a type of iron oxyhydroxide. You can see its chemical structure here. The important thing to realize about this is that it is one of these elements that is sparingly soluble, and it can precipitate from solution as an oxyhydroxide. It also takes charges which can flip their sign. Think back to the 0 point of charge discussion we had the week before last as a function of pH. And you can see how it can take either positive charges on its OHs or lose hydrogen ions and take minus charges. And this change happens around neutral pH, right? So when pH gets above that to basic pH, then it tends to get negatively charged, and at acidic pH, it tends to get positively charged. On the right-hand side is aluminum hydroxide. It's sitting there in octahedral coordination. The little dots are aluminums, and those bigger gray dots are meant to be oxygens that form the hydroxide groups, the OHs. And you can see that each aluminum is sharing multiple hydroxides with each neighboring aluminum. Now, this mineral gibbsite has no cation exchange capacity. Those oxygens don't really like to charge up very much at all. But interestingly enough, why gibbsite is important, and it forms under very, very extensive alteration of environments to make deposits. They're formed of gibbsite, but we call the deposits bauxite. I know it's a little bit complicated, but that's just the nature of the beast. But this layer is important because we're going to see that the gibbsite structure is one of the two primary layers that we find within clays. And on the next slide, I'm going to talk to you about clays as being either TO or TOT. And the O is going to stand for the octahedral coordination layer based on aluminum in the most common case. Because these are sheet-like or very open mineral structures, they're very flexible and relatively easy to have exchange into. Okay, so clay minerals come in two forms, and these forms are on the basis of alternating layers of silicon oxygen tetrahedra, one silicon with 4 oxygens arranged as a tetrahedron bound together, connected to an octahedral layer of the type that we just looked at on the last page, the gibbsite structure. So clays can come with one tetrahedral layer and one octahedral layer, which we call a 2TO or 2-layer clay. And that's the thing shown at the very top left of the diagram. Or a clay can be a three-layer clay, in which case we call it a TOT, which means it has both the octahedral layer that I'm pointing to there and two of those tetrahedral layers. Now, interestingly enough, if we think back to a couple slides ago where I talked about charge on these layers, the charge itself actually sits on the outside of these sandwiches on the red parts shown in this depiction here. And the more charge that we have on those layers, the farther apart the successive repeating layered units within the clay structure sit. So something that's really highly charged, like the mineral smectite, will have a greater interlayer separation, as I'm pointing to there, where we can fit more water, more cations, and even some organic matter. Because there's so much charge, these sandwiches, packets of mineral, push themselves farther apart. When the charge on the layers isn't as high as in the mineral illite or chlorite, then the layers tend to stick closer together and we can't fit as many cations in there. We tend to only fit the smaller ions. Now, I also want to make one other point, which is that there are also clay minerals where that yellow layer, the octahedral layer, is based on magnesium hydroxide, a mineral we call brucite. It's pretty rare at low temperature. It's more common in high temperature alterations, such as geothermal systems and so forth. So we're not going to really talk about it here, but it's useful to know. Now, these are three-dimensional perspective views of what on the upper part of the diagram is the octahedral layer, this sort of aluminum atom surrounded by 6 oxygens in the form of an octahedron, as well as the tetrahedral silicon surrounded by oxygens that I'm pointing to now. And the way those tetrahedral layers are made up is that all the basal oxygens, the ones that sit on the flat part of that pyramid on the bottom, they connect up with each other, making a sheet where that upper oxygen is sticking above. And when we combine that tetrahedral layer with an octahedral layer, we're basically taking all those oxygens that are sticking up in that layer of triangles and pyramids and poking them into that octahedral zone. So we can do that once across the whole layer to make the two-layer clay I'm pointing to there, or we can do it twice from the top and the bottom of the octahedral layer to make a three-layer clay. And these are the TO and TOT. And again, the charges sit on the bases of those tetrahedrons. And the more charge we have, the more the successive layers that come, these packets of TO or TO2, they sit in stacked packets. The closer or farther apart those are going to be, this is where water and interlayer exchangeable cations can sit. Now, I also sort of go through the stoichiometry of forming these minerals on this slide, just to point out that in a TO clay, we have a roughly 1-to-1 ratio of silicon to aluminum, but in a TOT clay, we have twice as much silicon as aluminum. And so you can usually tell from the chemical structure that if there's twice as much silicon as aluminum, it's probably a TOT clay. And that is described in a little bit more detail here. I've given you the pure forms of simple clays, kaolinite, which is a TO clay we've talked about a lot, and paraphyllite, which is a TOT clay, which we've talked about a lot. Now, the real mineral structures are a lot more complicated than that because of substitution, which we've talked about before, where we can replace some of the aluminum in the octahedral sheets with other elements, primarily silicon, and where we can take the silicon and replace it with a bunch of other things, such as some aluminum and some other elements. And this is what allows for the charge. So here I'm pointing to some of the very complicated structures of actual smectites, where you can see some of the substitution. For instance, if you look at smectite, you'll see that in the octahedral layer, it's got some aluminum and some magnesium. Okay, so now we want to think for a second about how do these types of materials, and clay minerals are one of the primary forms, but this is more general to other types of materials in the subsurface, including organic matter. How do they interact with things that are in solution? So we have two types of solutes, A and B here. So in the upper diagram, A can be free in solution, or it can be stuck onto the surface by either Coulombic, a charge-based interaction, or Lewis acid, Lewis base, a more of a van der Waals style interaction. And when it's stuck to the surface, we call that adsorbed. It can be adsorbed hard or it can be absorbed in a soft way, making it easier or more difficult to exchange. We also have the process of absorption, which is more of a chemical transition where A can be absorbed from solution into the mineral matrix and become a part of it. This is something that's usually harder to reverse, but not impossible. The third chemical reaction shown here is ion exchange, which we've talked about before. And if you see this example here, you see B is either stuck on the mineral surface or in the interior of the mineral, whereas A is in solution. And now I'm pointing to the opposite case where B is in solution and A is either stuck to the mineral surface or in the interior. So when we have the whole pantheon of chemical elements, they can all rearrange themselves. Some of them have a propensity to be either on the surface or in the interior, and some of them prefer to be out in solution. And clay particles can change their characteristics as a function of the composition of fluids, and fluids flowing through a system can change composition because of the exchange of ions between what is dissolved in water and what is stuck onto particle surfaces. And this will become a really important process when we talk about groundwater, but it's also a very important process in the formation of soils and the selectivity of some cations for staying around in soil columns, both important nutrient elements as well as contaminant elements like radioisotopes strontium-90 and cesium-134. So on this slide, I'm just talking about some of the actual substitutions that happen that give us the inner layer charge on clay minerals and other alteration minerals. The important thing to note is that if we take an ion and we replace it with something else in the mineral structure that fits roughly, it's got the same size, if it's got the same charge, we don't get any charge imbalance from that, and therefore no inner layer cation exchange capacity. But if we take something with a lower charge, so for instance, in the octahedral layer, if we take iron +2 or zinc +2 or lithium +1, and we replace aluminum +3 with that, those ions have less charge on them. That makes the mineral negative in charge imbalance. And what is the result is that other cations are drawn onto its surface to take their place. That is the nature of the charge buildup that counts for the cation exchange capacity, the CEC of clay minerals. So this is a diagram where I plotted across, or someone else has plotted across the x-axis, the sum of charges on a particle, and across the y-axis, the pH. And I want you to note a couple of things. First is that little squiggly line, which is a break in scale, so that the positive charges for the mineral smectite they would be way off this slide if we didn't have that break in scale. This is just to be able to make everything fit. And now if you look as a function of pH, if you look down around 0, we see two minerals. We see goethite, the iron oxyhydroxide I showed you the structure of several slides ago, and kaolinite, the very low CEC clay with almost no charge on its surface. Goethite, because it has a 0 point of charge around pH 7, changes the charge, but the charge is never very big, right? It's close to 0. There's a little bit of positive charge at low pH, a little bit of negative charge at high pH, whereas kaolinite is always negatively charged. Interestingly enough, as we raise the pH, we start to pull some of the hydrogen ions off the hydroxyls in the kaolinite structure and give it a little bit more negative charge, but it doesn't vary by very much as a function of pH. You can look at illite and smectite, and they show basically the same thing. pH doesn't really change the charge very much. The minerals themselves come with more charge because of greater amounts of substitution, because of less amounts of weathering in the formation. And at higher pH, they tend to have a little bit more charge. But this shows you the relative difference of the roles of pH and Bronsted acid-base exchange on charge versus mineral structure and ion substitution. It's the ion substitution that really generates most of the charge that we see on these clay surfaces. Okay, so now this is a slide showing you on average, this is not meant to describe any one particular soil, but on average, if you look at the relative amount of rainfall in an area, and you look at the weight percent of different minerals within a soil, you will see that the percentage of the minerals increases as the amount of rain increases, and the total percent of alteration mineral increases as the soil increases. So smectite is a low weathering product, clay, kaolinite is a high weathering product clay, and bauxite is basically deposits of gibbsite formed under very extreme amounts of weathering. We have very few deposits of bauxite here in Hawaii. The curve I'm pointing to now is the total amount of alteration mineral, which increases substantially as the amount of rain increases. And you can also see that what that alteration mineral is composed of transitions from one form to another as the rain increases. Okay, so this is a rather complicated diagram that's got a panel A and B. What's plotted against the bottom is aluminum, one of the two elements that really builds up very substantially and is present in large amounts and is relatively easy to analyze for in soils. So it's presented as a percent in weight of oxide. This goes back to the olden days when they used to basically heat rocks in a furnace and make them into oxidized forms of the minerals and then separate them chemically. And so you can see there aluminum increasing is really tracking the development of weathering. Okay, and then we have the percent of a bunch of other things on the y-axis. In the upper diagram, I'm showing you chemical elements, and in the bottom diagram, I'm showing you the minerals that they sit in. So one thing you will note is that almost every mineral on this diagram decreases as aluminum increases, right? You can see magnesium and sodium and calcium and potassium, as I'm pointing to, even silicon. But you will notice if you look carefully, titanium and iron increase. Now, this is in a saprolite zone where there's no organic matter present. So the increase of iron implies oxidizing conditions where iron is insoluble and therefore builds up. If we happen to be in reduced conditions, such as in a very organic rich soil, then iron would have the potential to be reduced and or solubilized by the organic matter and therefore not build up as much. Pretty much the other elements won't be affected that much. Now you can see I'm pointing to the difference between potassium in feldspar and plagioclase. These are two different feldspar minerals which sit at different parts of that Bowen's reaction series. The plagioclase breaks down really quickly. It's more susceptible to weathering. The potassium feldspar is less susceptible. And this is what accounts for the change in shapes of the sodium and calcium curves relative to potassium in the upper diagram. Potassium is released more slowly in alteration when it resides in a mineral that weathers more slowly, namely potassium feldspar. And this slide just kind of goes through some of the details for you. Okay, so those are solids. Now let's just talk for a moment about the soil water, the water that is present there. And what we find in the soil water is a function of what is the inorganic solubility of all the elements during soil formation, as we talked about several slides ago. Some things like to dissolve, some things don't, plus minus the role of organic matter, right? We have varying amounts of organic matter in the soil column, but in places where it is present, the sparingly soluble elements in the center of the periodic chart that sit around iron will be enhanced in solubility by the presence of organic matter, and so we'll find more of them in the soil water. And it stands to reason as we go down with depth, we will find less of them. Now, this is one example of how organic matter in a soil can help accelerate the rate breakdown. I'm pointing to several different common organic ligands that we find in the dissolved organic fraction. And you can see two examples. Ketchitol is just a diphenol compound. Two ways in which these molecules can help remove materials from solid minerals in the subsurface. One of them, the process of acidolysis, is taking a hydrogen ion that can be removed from the organic matter and using it to replace cations on a surface, liberating those cations into solution. The other is more of a complexation-chelation relationship where, for instance, in the Ketchitol structure, even though those hydrogens aren't particularly acidic, they do have a propensity to bind to iron and help solubilize it through a Lewis acid, Lewis base relationship. So now this is a kind of complicated diagram showing you 6 different chemical elements: copper, iron, chromium, zinc, magnesium, and calcium, plotted versus depth. Don't worry about those horizons yet, A, H, and B, and C, etc. But they're different depths within a soil column from top to bottom. What I really want you to notice here is 2 things. We're looking at a bunch of different bars, a series of histograms for different elements. Some elements increase in soil water as we go down, such as calcium, like I'm pointing to now. Other elements decrease as we go down with depth. These are things like copper or zinc or chromium, or to a lesser extent, magnesium. So some things build up in the saprolites, some things build up in the upper horizons. And as you might imagine, those things that build up in the upper horizons oftentimes have a lot to do with the differences in pH and organic matter that I talked about before. Now also look at the solid and hachures part of these bars. The solid part is the percentage that is complex, the complexation mostly requiring some organic matter present. And so we can see for some elements, for instance, calcium, it doesn't really care about complexation, whereas other elements like iron and chromium really depend on complexation to be present in solution at all. So there's these complicated relationships of what we will and won't find in soil water that is dependent on all these other co-varying characteristics that we're talking about, primarily pH and relative amount of organic matter. In this slide, you can read for yourself some of the details about each of these chemical elements if you wish. Can't remember what other incredibly interesting nuggets I was talking to you about here, but I'm going to wait until the next slide to say more. Okay, so now we're going to turn to the organic matter that we find in soils. As I mentioned, on average, they make up about 5%, but they can be a lot higher in some soils. And this is a list of some of the important things that organic matter does in soil. It sets the availability of nutrients, what we call preformed nutrients that microorganisms can act on and break down and liberate in the forms that plants can use again. It supports soil biota. It binds some organic materials, including contaminants like pesticides. It can also bind heavy metals and radionuclides. It can determine soil pH, and it can mediate mineral dissolution. Now, this slide shows you a little bit more example of how organic ligands can mediate mineral dissolution. And so you can see time plotted versus the amount in terms of mass transfer or rate of dissolution of the mineral quartz in the presence of different organic ligands. So water, acetate, salicylate, oxalate, and citrate. Acetate being the carboxylic acid anion of acetic acid. And you can see citrate, I've given you the structure up there. It's basically 3 acetates stuck to a central carbon. That is really effective at complexing and chelating the sort of surface metals in quartz, the surface, I should say, silicon atoms, and pulling them off and disaggregating. That bottom diagram kind of shows you a structural formula of how this happens. This is, kind of a van der Waals Lewis acid, Lewis base type interaction that allows for a much greater rate, something like a factor of 6 times faster dissolution just because it's present in the water. Now, there's a whole bunch of different types of organic compounds that we find in soils. This is just a table showing you some of the ones. Humic acids, which we've talked about before, the humic substances, things like fats and resins and waxes, which are not water soluble, but really affect how the wetting characteristics of soils, saccharides, especially polysaccharides, and then also nitrogen and phosphorus containing organic matter, which are the preformed versions of these nutrients, which are bioavailable for plants when they're transformed by microorganisms in the soil. There are other categories as well. Okay, so now for the last part, we're going to talk about the structural units within soils. And there's 2 different things on this slide. The first upper diagram talks about the water content in the porosity of the soils, the porosity being the spaces between the solid grains. And so the solid grains tend to be wetted in all but the most arid of environments, but the pukas, or the spaces themselves that make up the porosity, tend to be dry. In this upper zone of a soil, we call the vadose zone, or the unsaturated zone. That's where we see plant roots and we see most of the upper soil horizons of biological activity. At some point with depth, and this depends on the amount of water flowing through and the porosity of the soil, the rate at which water can drain through, we will reach a zone of saturation, the so-called water table. Various interesting things happen once we reach this horizon, such as the water becomes interconnected and it can flow through and start to leave the system and feed into groundwater. It can also, because it isn't exchanging with the atmosphere, get reducing and start to have reduced conditions via the redox ladder, driven by microorganisms and the high amount of organic matter in the soil column. We'll talk a little bit more about some of these water characteristics later, but I do want to point out that soils that are dry versus wet do have various characteristics that are, important for the ecosystems that they support. Now, the bottom diagram shows you the names of the structural units we find in soils. This is the kind of most generalized version. You can see soils have an upper horizon, so that's called the A zone, or topsoil, a B horizon, a C horizon, and bedrock. The C horizon looks most like the bedrock that it is formed from. Those are the saprolite layer, whereas the A horizon looks least like the bedrock. It also has the highest organic matter and it's the most acidic. And a lot of the action in soils happens in this B zone. As water percolates from top down through the system, it changes in composition as it goes through this B horizon, and accounting for the characteristic color and size fraction and chemistry of the B horizon. This is also sometimes called the zone of accumulation, because this is where, due to the change in pH and the change in organic matter content, we find precipitation minerals, the iron oxyhydroxides, the calcium carbonate, for instance, starting to accumulate. Now, it turns out that of these horizons, the A horizon is the most complex and tends to have many recognizable subhorizons. It's also true that, and I will show you a bunch of pictures in a moment, these horizons don't need to be as well developed in every soil or completely present or absent in every soil. So this slide just sort of emphasizes what I just said. The top of the soil is least like the rock that it came from. The bottom horizon is most like the rock it came from, and the B zone is intermediate. So these are just a couple of pictures that kind of go into a little bit more detail. One of them shows you textures, and one of them shows you the kind of more the relationship between the various horizons and things like tree roots and burrowing organisms like gophers and ants. And the key thing that you can see, and I don't even want you to memorize any of these names, but you'll see that that zone that I've kind of colored in brown, the sort of A zone, is almost always commonly formed up of multiple subhorizons, shown there in the table on the extreme right-hand side of the diagram as the O, the A, and the E. Sometimes you can find an H horizon. It's basically the relative amount of organic matter, the relative amount of kind of inorganic minerals, the amount of primary mineral grains and resistant minerals. And these are structures that form over time. So we might expect them to be better expressed in an older soil that has not been perturbed. For instance, an old growth forest. Human activities such as agriculture and the constant tilling of soils break up these horizons. And so we tend to see these things very poorly developed. We don't tend to in agricultural environments, go all the way down to the saprolite layer. So that C zone, which usually has a transition between weathered material and the bedrock from which it formed from, being kind of, generally well preserved in most soil horizons, even older ones. But those upper horizons tend to get mixed up and indistinguishable in a lot of agricultural soils. You can also imagine that an incipient soil, a young soil, is not going to have these horizons as well developed as we would find in an older, well-developed soil. And so, in fact, one of the ways that soils are characterized is by their age, which is measured oftentimes by how well expressed these different horizons are. The one thing that happens, and I mentioned this before, is the variation in the solubility of calcium carbonate. When calcium carbonate precipitates out of soils, we call it caliche. It's just a name of kind of a calcium carbonate rich layer in soils. And you can see here I've plotted, or they have plotted, depth on the y-axis versus the amount of rainfall on the x-axis. And what you find is this kind of swath of higher rain is a higher depth at which the calcium carbonate precipitates out. Now, calcium carbonate precipitates from a soil as two things happen: as the pH increases with depth and as the organic matter content decreases with depth. So the more rain, the more biological activity we tend to have on the surface, therefore the more organic matter, and therefore higher acidity or lower pH in the upper soil horizons. So the farther the soil water has to percolate down to the soil column to reach moderate pHs where calcium carbonate is no longer soluble and comes out of solution. I should also point out that most of the calcium in the calcium carbonate comes from breakdown of minerals in the rock, but most of the carbonate comes from the respiration of organic matter within the soils. Some of it obviously comes from the atmosphere as well, but we can get a lot of calcium carbonate that reaches saturation because we're producing bicarbonate as a function of respiration of organic matter in soils. There are other elements that can accumulate in this calcium carbonate zone too. So this is just a picture of what a caliche zone looks like. This one's really close to the surface. You can see this is an arid environment. This picture wasn't taken in Hawaii, but you would find the caliche horizon really close to the surface if you go to any of the dry areas, leeward coasts like Waianae or West Molokai, or northern part of Lanai, for instance. All these places have caliche relatively close to the surface. Whereas if you go to the windward areas like windward Ko'olau, where there are very thick soil horizons exposed and road cuts along the poly highway, for instance, you won't find caliche layers. They're oftentimes very, very deep down into the soil. So it's interesting because when these horizons form, they not only represent a change in chemistry, but they can also affect locally the porosity within the soil. A hard layer like this can help prevent water from percolating from top to bottom through that horizon, so they can affect the physical characteristics of the soil. For instance, how might a contaminant behave if it's spilled on that soil? So now the rest of the lecture is just some pictures of some soils, and a lot of them come from a particular soil scientist on LinkedIn who I follow. This is a really interesting soil. It's got all those upper horizons really well developed. You can see how dark and organic rich they are, and then they're overlying that kind of orange to yellowish color, which is the B zone, the zone of accumulation. It takes on that color because of the precipitation of the iron oxyhydroxides and the aluminum hydroxide and the lack of organic matter and all those things that we've been talking about. And you can see the depth, that's a bar in centimeters. This is a fairly well-developed kind of temperate region soil. Now, this is another soil that also has a classic topsoil, organic rich on the top, and then it goes into this sort of other horizons. They're all pointed out. These horizons are thicker here, but we still do eventually reach the B zone. And again, these well-developed structural units are not always found in all cases. This is an example, and I realize here in this resolution video, it doesn't look as good as it did in the lecture, but I think you can tell that this is a pretty homogeneous, bright orange, oxidized, low organic matter soil. This is formed in like typical tropical or subtropical wet environments. Now, this is a really interesting, very, very young soil. You can tell it's young because look at all those big rocks that are in there. This formed on top of rocks, a conglomerate deposit. So most of those big round things are rocks that are still full of primary minerals. And yet it's still able to develop an organic rich upper layer, then transitioning into the subsoil areas, and then down into the B zone horizons. This is an agricultural soil formed on in a humid area on very sandy substrate. And so you can see here a very homogeneous looking texture to the soil, but you can see an upper, more organic rich layer and clay and sand rich zone beneath it where there isn't as much organic layer. And we don't know how often this soil is tilled, but these layers can develop obviously relatively quickly. This is a humid temperate region soil, a clayey zone, where you can see the horizons are a little bit more subtle, but we can kind of see that darker quasi-organic rich layer up on top, much less organic matter than some of the other examples. And then a clay-rich zone at depth moving into the zone of accumulation. This is a more organic rich soil. It's wet, it's saturated. You can see it's got this consistently dark layer. I'm pointing out a horizon at depth where we're starting to see some precipitation minerals come out. But for whatever reason, the various upper A zone horizons are not very well developed here. And this is an extremely organic rich soil. This is a peaty soil. These form in places that are boggy, wet, saturated for most of the year. They can have up to 25% organic matter in them. And this is an arid environment soil where, again, it's not as oxidized as that earlier example, but you can see there are not very much in the way of structural units or compositional variation. It's a little bit darker at the surface and then becomes lighter at depth. These types of soils tend to have very low organic matter and they're well drained. So now I have a few slides that come from the CTAR website of different soils that we find in Hawaii, including the very oxidized and dry soils, soils of sort of intermediate organic matter content, and very organic rich differences, all like the sort of slides that we saw before. But interestingly enough, none of them have very well developed structural units where we can identify like very simply an upper horizon and the lower horizons. If you squint, you can start to see some variations, but they're not very well developed here. And this tends to be a characteristic of intensely weathered environments. So this is a slide. I don't want you to memorize any of these names. So I do want you to know that when soil scientists look at soil compositions, in addition to the rock type they come from, which also affects the names of soils, how developed a soil is, how well developed the horizons are, largely reflect the amount of time that has gone on. And so you can see in this diagram that there's an approximate sequence from very, very young soils on the left to very well-developed soils on the right, and intermediate soils in between. And some of those names, those different names up the middle, relate to the type of rock from which they formed, what we call the rock protolith. There are also, of course, climate factors thrown in here. But so I just want you to think about the fact that soils that have developed over a very long period of time are going to have more complexity, more structural variation, and more compositional variation than young soils. And this is just a table that you can read in the notes at your leisure if you want about some of the types of soils and what characterizes them, some of the different horizons that we find, variations in organic matter and pH, and the sort of thicknesses and abundances of important cations and so forth. And this diagram shows you the kind of way climate parameters affect soil composition as well. So there's a time component and there's a climate component, varying between hot and cold across the vertical zone and wet to dry across the horizontal. And so as you can imagine, you will find different types of soils with different colors and different organic matter contents for the given amount of time. They're going to vary as a function of how wet and dry and how hot and cold the setting from which they formed is. So you can take the same exact rock, like a volcanic rock here and in Iceland, and you're going to develop different kinds of soils on them at different rates because of these climate factors. And this is just another slide that you can, if you want to, you can click through to that website and learn a little bit more about all the different kinds of soils, how they are expressed in Hawaii. We have relatively simple rock type here in Hawaii. Most of our soils develop on volcanic rocks. And so really the differences in the soils are largely as a function of the climate factors, the water and temperature, which vary with elevation here in Hawaii, as well as the organic matter content. So it's really interesting because, for instance, the same type of rock can weather quickly or more slowly as you move through the islands from place to place. And this last slide just shows you an example of this. Is the island of Lanai. It sits in the rain shadow of Maui. I don't know if you've how many of you ever been there, but it's got this sort of most of the Lanai city sits at the edge of the old caldera of the volcano, and it's got this area of relatively steep-sided volcanic slopes in the kind of gray areas there. Those sort of squiggly lines in the kind of upper right of the map, those are really deep gullies. So, and Lanai Hale, which sits above Lanai City, is an area, an elevated area that's up in the rain shadow. It's got kind of, or non-rain shadow, it's got kind of a cloud forest. It's the only place on the island with a significant rainfall. But what you see is a variation in soil type. So if the caldera, which is what I was just pointing to there, has the red and the blue types. These are old soils that have accumulated there over a long period of time. And of course, this area was heavily farmed by Dole pineapple, which later became Castle and Cook. This was their primary first pineapple plantation. It was still under cultivation until the early 90s. And so the soils are heavily agriculturally amended there. But when you get onto the steeper slopes of the kind of north and east facing parts of the islands, we tend to find younger soils that form on these places that are slightly wetter and with steeper slopes where the weathering products are continually washing away, giving us the ability to kind of refresh and regenerate and make younger soils in this location. One example that I mentioned in class on one of the earlier slides, which I didn't mention here, is that we can look at young and old lava flows on Mauna Loa volcano and look at the rate of difference of weathering when we go from the windward side, like the Hilo side, to the Kona side, the leeward side. And, lava flows from the 1850s look like they just formed yesterday in the leeward case, and on the windward case, they can be very substantially covered with soils. And so that's just a difference of what can happen in 150, 170 years with differences in rainfall. The other thing I'm pointing out here at the end is just to remind you that you have new reading for this week and next, chapters 14 and 15 of Manahan. So please do them, pace yourself. There will be a homework assignment associated with these things. And I think now I'm asking for questions, and I didn't get any.